Hello, my name is Koshtura, and today we will talk about my second presentation for term paper. First, I want to talk about the problem statement. With environmental issues and health becoming trending topics, usage of bicycles as a mode of transportation has gained traction in recent years. To encourage bike usage, cities across the world have successfully rolled out bike-sharing programs. Under such schemes, riders can ride bicycles using manual automated kiosks spread across the city for defined periods. In most cases, riders can pick up bikes from one location and route them to any other designated place. The bike-sharing platforms from across the world are hotspots for all sorts of data, ranging from travel time, start and end location, demographics of riders, and so on. This data, along with alternate sources of information such as weather, traffic, terrain, and so on, makes it an attractive proposition for different research areas. About exploratory data analysis, we will talk in the first presentation. In this presentation, I will talk about correlations, regression analysis, testing, and training. So, correlations. Correlations help us understand relationships between different attributes of the data. Since this term paper, I will focus on forecasting correlations that can help me understand and exploit relationships to build better models. So the next snippet prepares correlation metrics using the pandas utility function correlation score from Python. This correlation matrix showing values in the lower triangle form on an orange and black gradient from negative to positive correlation. As we can see, the two count variables registered and casual show obvious strong correlations to total count. Similarly, temp and temp show high correlation. Wind speed and humidity have slight negative correlation. Overall, none of the attributes show high correlation statistics. And now we will talk about modeling. It is the most important part in my term paper. The dataset was analyzed and certain transformations like renaming attributes and typecasting were performed earlier in the term paper. Since the dataset contains multiple categorical variables, it is imperative that I encode the nominal ones before I use them in my modeling process. So now I want to demonstrate to you some mathematical analysis, some regression analysis and residual analysis. So we will talk about linear regression. One of the simplest regression analysis techniques is linear regression. In this equation, y is a dependent variable, x is the independent variable. The symbol denotes the intercept of the regression line, and b is the slope of it. So the next one, it is the ordinary least squares criterion, where q is the total squared error, and in this function I minimize the total error to get the slope and intercept of the best fitting line. So we came to the training. So what it is? Now I will have the background of linear regression, and I will get started with the model building. The linear regression model is exposed through scikit-learn's linear model module, of course Python. Like all machine learning algorithms in scikit, this also works on the familiar fit and predict functions theme. The following snippet prepares the linear regression object for us. And this is Normality Test. Here we use scatterplot to analyze our predictions. The following snippet uses matplotlib to generate scatterplot between residuals and observed values. Distribution and trends. The dataset after preprocessing, which I performed in the previous presentation, is ready for some visual inspection. I begin with visualizing hourly ridership counts across the seasons. The following snippet uses Seaborn spine point plot to visualize the same. So, in these diagrams, we can see similar trends for all seasons, with counts peaking in the morning between 7–9 am and in the evening between 4–6 pm. Possibly due to high movement during start and end of office hours. The counts are lowest for the spring season, while fall sees highest riders across all 24 hours. Similarly, distribution of ridership across day of the week also present interesting trends of high usage during afternoon hours or weekends, while weekdays see high usage during mornings and evenings. This we can see on the second diagram. The generated bar plot showcases a defined trend in ridership based on months of the year. The months June–September see highest ridership. On this bar plot, we can see the color green and blue. It is June, July, September, August. It is a high trend on the bike sharing. And normality test, QQ plot. This is a visual graphical test to check for normality of the data. This test helped me identify outliers, skewness, and so on. The test is performed by plotting the data versus theoretical quantiles. The same data is also plotted on a histogram to confirm normality, and this is shown on these pictures. So now we will talk about decision tree-based regression. Decision trees are supervised learning algorithms used for both regression and classification problems. They are simple yet powerful in modeling non-literal relationships. Being a non-parametric model, the aim of this algorithm is to learn a model that can predict outcomes based on simple decision rules, for instance, if-else conditions based on features. The interpretability of decision trees makes them even more lucrative, as we can visualize the rules it has inferred from the data. We explain the concepts and methodologies related to decision trees using an example. Suppose I have a hypothetical dataset of bike models from different manufacturers. Assume each data point has features like capacity, price, year of purchase, miles driven, and count. Given this data, we need a model that can predict the mileage given other attributes. Decision trees work in a top-down manner, and non-splitting is an important concept for any decision tree algorithm. Most algorithms follow a greedy approach to divide the input space into subsets. The basic process in simple terms is to try and split data points using different attributes, features, and test against a cost function. The split resulting in a least cost is selected at every step. Classification and regression problems use different set of cost functions. Some of the most common ones are as follows, and we can see it at this diagram or table. As I mentioned, decision trees follow greedy recursive splitting of nodes, but how when do they stop? There are many strategies applied to define the stopping criteria, the most common being the minimum count of data points. Node splitting is stopped if further splitting would violate this constraint. Another constraint used in the depth of the tree. And decision trees have been around for quite some time now. They have evolved with improvements in algorithms based on different techniques of the year. and we can see the decision tree algorithm. While exploring and learning about any dataset, it is imperative that we check for extreme and unlikely values.